Hello, I am Andy Martin from Control Plane. A little bit about myself. I have a background in security development and operations. I'm also CISO at Open UK, a charity aimed to advance the use of open source in government and the private sector in the UK and fairly remunerate open source maintainers. And I'm co-chair of the CNCF Technical Advisory Group on Security. And Rahul, good to see you today. Could you introduce yourself?
Hey, Andy, very nice to meet you. I've been in the security domain, but my primary background has been into network and transport optimization. And for the most part, security goes hand in hand with some of those elements. You have TLS, you have cybersecurity issues with regards to transport and network. So, for the past couple of decades, I've been working primarily from multi-part transports, improving transports for streaming purpose and things like that. And currently, I'm one of the maintainers of KubeArmor, an active participant in CNCF, presented in KubeCon last couple of times. Very interested in having this discussion. Looking forward to connect with a wider audience here.
Fantastic. Well, KubeArmor is a hot new project. Perhaps you could talk a little bit about the background, please.
Yeah, so it all started when we were looking at MITRE TTPs, MITRE attack tactics, techniques, and procedures. And when we found some of the elements, in the TTPs, right beneath the techniques, there are mitigation strategies that were mentioned. And we were trying to check for tools which can handle those kind of mitigation techniques from the defense perspective. And we found that in the Kubernetes world, especially from the pod hardening perspective, there was nothing that was in place. Yes, there were tools which can do observability and figure out if some things have changed or if something has been modified. But the real intention of some of those mitigation techniques were to actually, stop the attack in the first place. I'm going to share my, screen just to, explain one of the sample MITRE attack TTPs, a very simple attack wherein the attacker, once the attacker gets a leverage within the pod, attacker will try to update the root certificate. And once, if someone is able to update the root certificate, it's possible to actually do a man-in-the-middle attack. It's possible to, sniff all the traffic. It's possible to not come into the eye because of, there is no TLS problem that is going to be detected once the attacker manages to install it. And the mitigation technique for this is pretty straightforward, saying that, ideally you should not be allowing anyone to update the root certificate folder. Root certificate folders exist on an operating system. It is specified pretty far. This is one of the examples. There are many such examples. The other example that I can quote is dynamic package management tools. No one wants to use dynamic package management tools such as apt, YAM, DNF, APK at runtime in the production environment because it can introduce drift in your workloads. But most of the container images ship it along with the base image. It could be Alpine, it could be Ubuntu, it could be Debian. And how do you, stop these kind of, how can you put constraints on some of these tools is where KubeArmor started. So the primary aim for KubeArmor was not only to observe the malicious intent, but to also do inline remediation. And inline remediation is exactly where it shines. So that is where that is. So we had been discussing, this was, it goes way back in 2020 when Suchakra Sharma, one of the leads in Shift Left Security, Jehun Nam and myself were discussing about how do we handle this? What are the existing techniques available in Kubernetes? And we found that there are existing techniques, but there are pitfalls and we could possibly do something about it. We created a prototype, it made sense, we decided to go ahead with full-blown implementation. And very soon, within 6 months, we decided to go the CNCF route. And that was one of the best decisions that we took, applying for CNCF Sandbox. I think, the kind of feedback we got and the kind of attention to the problem statement we got was immense. And it's always good to discuss with the wider audience when you have a problem statement which is niche in the first place. Yeah.
Yes, I strongly agree. It's so nice to hear that the community has been reciprocally beneficial. Obviously, as a strong CNCF advocate, I'm very strongly supportive. So you talk about some of the pitfalls that you had to overcome with existing projects, especially around addressing those MITRE attack methods and TTPs. What was the current state of the art with existing projects when you came to appraise the landscape?
Yeah, so let me explain. So I'm going to skim through some of the slides here. Please don't mind, just going to pop up some of the slides. So if you see, we already have something called a pod security context in the Kubernetes world, where an administrator, a user, can specify an AppArmor or SLNS policy and set the annotations equivalently. AppArmor is getting to stable release, by the way, in the new Kubernetes version. The challenge that we saw is that how would one come up with an AppArmor policy or an SLNX policy? And in the future, there's something called as BPF LSM coming into place, which does not have a predefined syntactical element in place. How do you leverage these tools without having the complexity of dealing with the language primitives of AppArmor and SLNX? It's extremely difficult. If one does not understand SLNX and tries to create a policy out of SLNX, there are more chances that they will get things wrong and go down a rabbit hole of fixing unwanted things, and in the end, opening up a lot of security holes. So essentially, one of the aim for KubeArmor was to do inline remediation, and to achieve that, abstract away all the internal complexities of AppArmor, SLNX, and BPF LSM, provide an easier to use interface. And an example is given here. For KubeArmor, you can specify a YAML policy like this, and internally KubeArmor will see what is the prevalent, what is the deployed LSM on that particular node, converted it accordingly. For example, for AppArmor, then there is this particular language that it automatically converts. If it is BPF LSM, it dynamically generates the EVPF bytecode. Similarly for SLMX. So that is what. So essentially, at the end of the day, the user has to deal with the YAML, specify easy to use language constructs, and the user should be done. We have taken it actually to the next level, where even this part is automatically generated, wherein we have a component in place along with KubeArmor, which can take KubeArmor's visibility and auto-generate these policies as well. So essentially, our aim or our vision has been for the KubeArmor has been to make runtime easier to deploy from the zero trust perspective. And it is especially difficult to get it right, because if you do not have the right primitives in place, you might end up taking the application down, because even if you are denying something very basic, like a file access for an application, there are good chances that the application will stop working. So how do you avoid all those things? And that's the final aim of KubeArmor and some of the accessory tooling around KubeArmor.
And it's very interesting that you're one of the first projects to utilize that BPF LSM. Of course, eBPF is a reasonably recent technology that has seen huge adoption across multiple different dimensions, from networking through into security. How do you find the prevalence of BPF or eBPF compatible kernels across the major cloud providers at this time?
That's a very good question. In fact, we did a survey, an analysis of which all kernels are actually BPF compatible. So we didn't want it to try out something new, and we saw one particular pattern. We cannot depend upon a security primitive which is not available. And you see, BPF LSM today is not available in many of them, but any new version, right? Any new version. So if you see, most of the kernel versions above 5.8 and above already have BPF LSM. Bottle Rocket already ships with 5.10. GKE COS, container optimized OS, ships with kernel version 5.10 and above, 5.8 actually. So what we are seeing is almost any new image that is getting shipped is getting by default enabled with BPF LSM. And one advantage with BPF LSM is that it is a stackable LSM, unlike AppArmor and SLNX, which means that you can stack BPF LSM on top of AppArmor and SLNX. So you get that double protection in a way that will that makes the job of KubeArmor even simpler, because you now have the flexibility of eBPF at your disposal. you have the right hook points in the form of LSMs, and you still have the base protection in the form of AppArmor and SLMs. So you get a multi-layer defense, advantage, and that we have put in a lot of thoughts before starting our work on BPF LSM. But you're right, we KubeArmor is one of the first engines to actually leverage BPF LSM. We recently wrote a blog which on AWS Bottle Rocket, which got immense attention in the Bottle Rocket community as well, and we are looking forward to trying out KubeArmor with BPF LSM on many more other operating systems.
And it's fantastic. Obviously, huge thanks to everybody who has been working on building those stackable LSMs. The advantage of protecting against potential vulnerability fundamentally in the kernel implementation, backed by a secondary security system, really, as you say, that defense in depth is it really helps to harden the runtime against 0 days and unknowns. So that's fantastic. Okay, could you perhaps talk a little bit about the key architectural elements of KubeArmor and how that? I'm going to say that again.
Yeah. So yeah, it's the approach that differentiates KubeArmor from other engines, is what we believe. And we have put in a lot of thoughts about what is the approach that are available. Now, again, I'm going to just skim through some of the approaches that are available. So some of the enforcement.
I'm sorry to interrupt. I'll say that again. I think I got the question too messed up to. I was going to let you carry on. So I apologize. Let's start that again.
Yeah.
Perhaps you could talk about the key architectural elements that differentiates KubeArmor from other solutions.
Yeah, that's a great question, actually. And this is where some of our initial brainstorming and thoughts went into as to what is the approach that we'll choose. We wanted an approach which could do inline remediation, which means that we do not want an attacker to execute their code, which means that even before an executable is found, we wanted an ability to not allow that executable to be forked in the first place. And we didn't want it to change anything within the container image, because changing into the container image is a big no. It changes the container integrity with supply chain security policies in place. It's impossible. And I've seen a lot of approaches out there which actually makes changes into the container images. Each of it has its own pros and cons, but I feel that is a big no. Everything from FIP certification to most of the compliance goes for a toss the moment you start changing the container image. So our vision from day one was that we want something which is completely transparent to the application. We don't want the application to change, and we wanted to use most of the Kubernetes constructs. So essentially, KubeArmor today deploys itself as a daemon set, and on the design element, it makes use of two things. One, it makes use of LSMs, like I said, AppArmor, SLNX, and BPF LSM for enforcement perspective. But any security engine also needs visibility, right? And for visibility, we use eBPF. Again, using eBPF for visibility observability is not a new thing. A lot of tools exist out there. Our intention with this visibility was to not give very raw data, not send raw data to the user space. We want to make sure that we focus on security elements, security constructs, and then make use of for LSM policy generation. That was our focus right from day one. And you can see here we use eBPF to knit kernel event with the Kubernetes and container metadata. Based on that visibility, we ought to create a security policy, and that security policy is essentially enforced by using LSMs. So eBPF, LSMs are the key architectural elements. Along with that, we are making use of Kubernetes orchestration, orchestration elements. For example, KubeArmor policy is a custom resource definition. You can actually specify. Let me show a sample KubeArmor policies. You can see here that a KubeArmor policy itself is a CRD. It's a Kubernetes resource, and this resource is handled by the KubeArmor daemon set to orchestrate the policy. So that's and again, like I said, there are a lot of approaches available out there, including LSM hooks, which is what we have chosen. This custom kernel module, one can use custom kernel module, but that's a big no, because no one will allow you to insert a custom kernel module in the production environment because of the risks associated. There's BPF send signal, and I see Tetragon making use of BPF send signal today. Maybe so essentially, they from the kernel space you can go and kill the process. Then the seccomp notify, BPF override return. Seccomp notify is limited by based on what it can do. BPF override return is not available in most of the operating system, and even if it is available, it has limitations in terms of how the kernel calls this API. So if the kernel execution is preempted, there is a chance that this API will never get called. So the risk associated with this. And in the user space, of course, there's LD preload. Again, LD preload is a technique that is widely used out there for various other purposes, but for security, it's not a good idea because you have to insert a dynamic library within the container image, which is a big no. Ptrace is another option, but again, Ptrace has a huge performance overhead, runtime overhead. It's going to slow down your application by 50 to 80%. I've seen an approach where glibc is overridden, so you can change the libc library in the container image. That's a big problem because your FIPS certification, your container integrity, everything goes for it. And then there is a different approach altogether, like sandboxing technique in the form of gvisor and Firecracker, where gvisor actually creates a sentry system called entry through itself. So all the system calls actually pass through gvisor, but it's very intrusive. It gives you a lot of flexibility, but it expects you to make changes on the host and the container runtime, which is a big no in a lot of deployments for us. So eventually what we figured out is the LSM hooks are the right way to implement, and LSM hooks have been used for past couple of decades for host hardening. But and even in the Kubernetes world, it was available, but essentially in its native form, in the form of AppArmor and SLNX, with KubeArmor, we are like I said before, our intention was to abstract away that complexity and introduce new security primitives in the form of BPF, which was not present in the pod security. So that is a background of some of the architectural elements and design elements that we thought of.
And it's certainly worth not overly relying on those sandboxing functionalities or next generation runtimes. While they provide a huge amount of isolation value, they do add some difficulty for a developer. It's things are not quite as they seem in some cases. So yeah, certainly for very hardened deployments, I can understand those uses, but certainly in the general sense, they become very difficult to use effectively. So thank you for running through that. That's very interesting indeed.
Thank you.
How then are these approaches different from what we see more generally in open source tooling?
Okay, so one of the approach, let me give you an idea about one of the approach that we see. So most of the tooling out there are based on eBPF alone, and eBPF is great, but it does not allow you to enforce some of the settings. Like it can observe things, and it can enforce in a lot of context. But let's say, for example, eBPF alone cannot actually stop a process from getting poked. Let's say, for example, that is an example. So most of the existing engines, what they're doing is you identify a process, you identify a malicious intent, and then you go into a remedial action in the form of killing that process. But there is a time difference between the malicious intent is identified and the killing of the process, and between that, a lot of things can go wrong. Your attacker has a chance to now execute that code, which means they can now switch off the security knobs. And we have seen these kind of attacks before, where the first thing that the attacker does is once they get an ability to execute in the workload is to switch off all the security knobs, which means that even if by the time you go and try to kill the process, a lot of things might have already changed within the workloads, or they might have already impacted, or they might have deleted some of the files or important folders or sensitive assets within your workloads. There are a lot of possibilities. So that is why the way in which LSMs differ is the checks are in line, which means that even before a process is forked, It goes and checks whether a process should be allowed to be forked based on certain conditions, which are specified to the KubeArmor policy. And that is a fundamentally different approach. So essentially what we're doing is we are reducing the attack surface, not trying to do post-attack mitigation is how I would like to put it.
And that's very interesting because, of course, eBPF is, as you said, normally regarded as an asynchronous technology because it was shipped for networking and observability within the kernel. Then this synchronous inline LSM control really is an interesting new differentiator from what we have at the moment.
Right.
Okay, fantastic. So in terms of potential use cases, where do you see the possible deployment of KubeArmor?
Yeah, again, we started off with Kubernetes native solution in the first place for KubeArmor, but then we extended our goals to some of the legacy systems as well, in the sense that KubeArmor today deploys, in the Kubernetes world, it deploys as a daemon set. But if you have pure containerized workloads, it can be deployed as a systemd process or as a container to protect pure container, or if you have virtual machines and bare metal based workloads, legacy workloads, and you want to still use the same policies and abstract away all the complexities of LSMs like AppArmor and SLNFs on the regular host, you still can use KubeArmor. So all these three modes are protected. And what we have seen is, Kubernetes is getting adopted across the spectrum. We see 5G control plane, the near real-time intelligent controller in 5G control plane, adopting Kubernetes, ONOS, micro ONOS as the platform for orchestration. Similarly, on the edge, we see LF Edge Open Horizon using Kubernetes orchestration for deploying edge workloads. Similarly, Intel Smart Edge. And there are numerous other activities. In fact, we see Kubernetes reaching almost to the far edge, in some scenarios. So our deployments, even though we started with cloud security, our aim was to secure cloud-based deployment, cloud Kubernetes deployment. Very soon, we added functionality to protect EC2 instances, and then we also have done a POC with Open Horizon, LF Edge Open Horizon project, and maybe I can show you. So this is what an Open Horizon project looks like. There is a management hub, there is an edge, and you get all the visibility as to what the workloads are doing. And the primary aim there is that you have all these Docker containers, and these Docker containers are workloads from different vendors. Now, how do you ensure that a security hole in one of the vendors' workload does not impact the edge as a whole or other workloads on the same edge node? So that was our prime intention with KubeArmor, to do container isolation. And this particular use case is flying off very well with edge, because almost security is one of the burning issues on the edge side and in the 5G control plane. And KubeArmor could be a good solutions to that. So container isolation today is done either using AppArmor and SLNX policies, which are extremely difficult to deploy, and basically KubeArmor automates that whole process. So yeah, cloud security is what we started off with. We also have edge deployments now, and we are also, we are now part of 5G Open Innovation Labs, where we are trying several other 5G control planes deployment.
Wonderful. Okay, thank you. So you've been working in open source. This is submitted to the CNCF. It will pass through tag security as a demo, and looking for feedback from the community there as well. But this is open core for a product that will come with some commercial assurance as well. Can you speak a little bit about the difference between the AccuKnox version and the KubeArmor open source?
Yeah, so let me first explain that currently we do not maintain an upstream fork of KubeArmor in AccuKnox. So the open source is exactly the same as what is available in enterprise. In the enterprise version, what we have essentially done is simplified the whole process. Like you have policy discovery in place. You need to do dry run or audit mode handling for certain namespaces, certain other namespaces. You have to automate how do you handle alerts and logs. You have multi-cluster deployment, orchestration of policies. So using GitOps for policy management, all the other things. So simplifying this policy management and enforcement across multiple clusters and making the discovery of policy much more simplified is what we have targeted in the enterprise version. However, the core enforcement engine remains the same in enterprise edition as well. So anyone who contributes to KubeArmor, the whole thing goes out there in open source. So that's the primary differentiation between the enterprise and the open source version. That in the enterprise, we are essentially simplifying some of these user journeys. Like you have a workload in place, you want to auto discover a security posture, you want the security team and developers to look at what's happening in their workload, and then allow the security administrator to enforce that security posture to get into zero trust mode, wherein only the defined or identified application behavior will be allowed to execute. So that is something that we have simplified in the enterprise version.
Wonderful. And in conclusion, when might we expect a generally available release? Is this suitable for people to start using for enforcement today? What's your feeling?
So KubeArmor is already in stable release. But AccuKnox as an enterprise product, we're going to have a general GA release by the end of this year, in month and a half from now, and we are working very hard towards that. Right now, as you can see, any GA release is extremely hard to get. 100% of our efforts are focused towards that currently.
Fantastic. Well, thank you very much. Is there anything else you'd like to add?
Thank you very much, Andrew, for giving me the chance to talk to the wider community. Again, KubeArmor is an open source in CNCF. It's a sandbox project. We have got steady attention from the community. We want to make sure that the problem statement is understood by the community. We see that the problem statement is now spoken out loud in NIST and other compliance frameworks. We want to make sure that we reach the wider audience through the open source. So anyone who wants to contribute towards KubeArmor, please have a look. We'd be more than happy to engage you on our Slack groups and in the GitHub pull requests.
Excellent. Thank you very much, and the best of luck as you career towards the end of your GA.
Thank you. Thank you very much, Andrew. It was a pleasure speaking to you and reaching out to this community. Thank you very much. Thank you.
Thank you too.